Jim is one of the last scientists from Bell Labs living in Murray Hill. So Jim, it's all yours. Thank you, sir.
So I have a fairly serious talk today, and then you get the dessert later. But this really is addressed mainly to the students, and I want to talk about something, what's happening now and what's going to happen in the future. Now, there are lots of futurologists around, and there are all kinds of futures ahead of us, but the future I'm interested in is the future that is available to you because you're at NJIT. And we're going to talk about how the world is changing and how you can use NJIT, you're already here and you're smart enough to be here, how you can use it to get into that world. We're going to talk about, in particular, the world of big data. So let's see. Aha, here we go. We're going to start off with a few stories, and we're going to talk about the point of view from a theoretical physicist, which is what I am, but it actually applies to all of science, and much more, in fact. So it's about big data. Here we go. Okay, right. Big data means that some people say, swamped by data. I like to think of the world of big data as a great opportunity. And we're going to see how, I'm not going to talk about how everybody is using it. In particular, I'm not going to talk about how the hedge fund people used it. But I'm going to talk about how I used it because that's what I know about. But you can see some analogies in what I've done with what the opportunities that big data offer to young people today. So I'm going to start out with Alice's parables. Of course, Alice is Alice in Wonderland. And Lewis Carroll anticipated a lot of modern events. And if you read Alice in Wonderland with a lot of imagination, you'll see all of those things happening. So our one of the things that physicists worry about is there's nothing left to do. And this is not a new idea, as it says here. You have this famous story about the Mad Hatter's Tea Party. And so it's written out here. I won't read it to you, but you'll notice that Alice arrives at this tea party, and it's going on. And there are some funny jokes in here about the people talking, two guys sitting at the table and talking over the head of the dormouse who's asleep. That kind of thing happens at dinner often, and that's exactly what happens. So the first thing they say is, when they see her coming, there's no room. There's no room at the table. They're all crowded together. But actually, it's a big table, and there's lots of room. And the moral to that is, there are lots of things for you to do, but not necessarily at the end of the table where everybody is. In other words, you have to think of new things to do that you can do with big data. And that's what we're going to come to. And of course, other people, especially older people like myself, are saying, no, it's just too much, just too much. And as Alice, this is one of the more famous things in Alice, that the Queen says, you have to run as fast as you can just to stay where you are. And if you want to go anywhere new, you have to run twice as fast. Well, we're going to see how big data enables you to do that. In other words, the people who've been running as fast as they can to stay where they are the people who've been living in the world of small data. The opportunities that lie ahead of us now are to run faster by taking advantage of big data. So big data does bring new problems. And now I'm going to get a little technical. Most of the physics that you will study in the books, I'm not knocking it, it's beautiful stuff, I love it, it's all mine. I mean, I lived with it, right? But it does use polynomial methods. Now, modern mathematics says that there are many polynomial methods which are suited to dealing with small data. But now we recognize that there are many problems which mathematicians call non-polynomial complete, which they abbreviate actually is NPC, it's trade jargon, but it means that you can't do them, solve them, using only polynomials. And of course, in the old days, we used to say, well, if you can't do it with polynomials, that's statistics, and you turn it over to statisticians. And I don't want to knock statistics, but the standard statistical methods that we're familiar with and that you see in the books are really designed to handle small data. They're not designed to handle big data. It's not that they're not useful, they're very useful, but they're just getting you started. If you want to go on and do big data, you have to do more than you did before. So, and the reason these general methods from statistics are a little inadequate is they assume that the database that you're looking at is basically random in some sense. But nothing out there in the real world is random. Not really. It's just you don't know what's going on. That's a different thing than saying random. People often use the word random to mean I don't know. That doesn't, there's a lot going on, you just haven't figured it out yet. And some of my colleagues, a very famous one is Murray Gell-Mann, a very famous particle theorist. When he retired, he went to Santa Fe and set up the Santa Fe Complexity Institute because he realized that this world of big data is a complex world and you need better methods of addressing it. Unfortunately, he surrounded himself mostly with statisticians, and they haven't gotten very far because they don't really understand big data. They're statisticians, and scientists go a little further. So we're going to talk about a family of problems. And the specific family we're going to talk about, I used to work for the telephone company, you have to know, is networks, self-organized, compacted networks. That's a lot of technical jargon, but it might help you in thinking about self-organized, compacted networks to realize that you're made out of proteins, and proteins are self-organized, compacted networks. So when I talk about that jargon, I'm talking about how you manage to be alive. Okay, self-organized, compacted, non-polynomial complete networks. Very complicated. In fact, you are very complicated. So I decided not to start out with that problem. I'm a coward. So there was a principle that I learned from Bill Shockley, and if that name doesn't ring a bell, I should mention he invented the transistor, on which everything relies today. Anyway, Bill Shockley's principle was solve the simplest problem first. Don't start out with something complicated. Find the simplest problem, find a way to solve it, build a platform, and go from there. So I decided to start out with the simplest self-organized, compacted, non-polynomial complete. They're network glasses, like window glass. That turns out to be a very hard problem. You see window glass all around you. They build skyscrapers out of it, but working out a theory of window glass is very hard because the atoms in window glass are not arranged periodically the way they're on crystals on a lattice. They're off lattice, and that means they cannot be studied. Structure of glasses cannot be studied using the standard method we use for crystals, which is X-ray diffraction. That doesn't work very well for glasses. And so this problem remained basically considered to be a non-problem, that is to say we don't know how to solve it, for 1,000 years. And there were a lot of problems. And I decided I could ask some simple questions, namely, can't we find some configuration coordinates that explain the phase diagrams of network glasses? We could discuss how reversible their glass transitions are. These are basic questions. Particular reversibility is at the heart of thermodynamics and statistical mechanics. And in particular, point 3, many networks exhibit what are called fat tail or black swan statistics, non-Gaussian statistics with a long tail. Some people say, from Wall Street, say that, well, it's true we just had this tremendous financial collapse, but we were using a perfectly good Gaussian model, and we were sort of shot down by the fact that it didn't quite work well enough, and there were these fat tail or black swan effects, otherwise known as kaplooey, right? They were doing fine for 10 years, and then something went wrong, and all of a sudden kaplooey. So now, so that's the network glasses. The same thing happens, as I say, in financial networks, but I just working on the simplest case, the network glasses. I also extended these ideas to a field called high-temperature superconductivity, which you may or may not have heard of, but it's been a big thing in science over the last 25 years. And what you do is a superconductor, of course, carries current without dissipation, and the question is below a certain transition temperature, and these transition temperatures are much higher in these certain ceramic materials than they are in ordinary metals, 5 to even 100 times higher. So they're very high. And finally, we come down to this point that I mentioned before. Proteins, in fact, are also examples of self-organized compacted networks, and they are compacted by interaction with water. They start out as long chains, but when you put the chains in water, they fold up into globules, and the water sort of presses them into this funny globular shape. And if you've ever seen pictures of protein crystal structures, they look very complicated. In fact, they are very complicated. But they, can we do something to quantify how they've been compacted by their interaction with water? And so on. So that was the idea, and let's go on. So then I began to work on these phase diagrams, and the problem is there's a technical problem here. And the technical problem is that when you quench them, they don't, as I say, form nice crystals, and they're not really in equilibrium, but they're almost in equilibrium. They will stay in the quenched configuration for a very long time. For instance, window glass, if you just throw it out in the garbage and it doesn't get heated too much, it'll last, I have no idea how long, millions, jillions of years, and it's still not in equilibrium. And the idea I had was that the internal pressures, which are the key to understanding the stability of these network glasses, are done by, can be explained in terms of something that theoretical physicists love, and that is Lagrangian constraints. Now that may sound complicated, but you're familiar with Lagrangian constraints already. If you have a ball rolling down an inclined plane without slipping, the constraint is that it rolls without slipping, right? And if you did a little homework problem, and I'm very big on homework problems, you would have found out that using the mathematics of Lagrangian constraints, you can solve this problem of the ball rolling down the inclined plane without slipping much more easily than you would if you didn't use his methods, that's about 1780, and instead relied on the methods of Newton, which is about 1630. So between 1630 and 1780, you had about 150 years, and Lagrange came up with this wonderful idea. It's one of the prettiest ideas in theoretical physics, and what I liked about it was I could take Lagrange's idea with the balls rolling down and apply it to network glasses. And we won't go into details of how I did that. It took me about 5 years to get that idea. Wasn't easy, and about 30 years to develop it. But it works, and it's all connected with these networks, and you begin to have a feeling for networks. And as I say, I used to work for the telephone company, and we loved networks. We still do. The internet, of course, is something that everybody takes for granted, but those of us that grew up before the internet see it as a marvelous realization of all the things that we were working on in the connection of networks. So this gives some details about how we do this. We count the number of Lagrangian constraints. We match it to the number of degrees of freedom. These are all basic ideas of theoretical physics. And we work out a model that explains the phase diagrams as you vary the average coordination number, and it works out. And this is an example of solving an impossible problem, namely a non-polynomial complete problem, explaining the phase diagrams of glasses, including window glass. Okay, so we did that, and it's a lot of fun. Once, as I say, it took me 5 years to get started, but after I got started, it was a lot of fun. And once you get into these impossible problems, you can't put them down because you begin to see that you don't have to be afraid. All you have to do is sort of look at them and think about the data and ask what are the simplest possible things, follow Shockley's principles, and you will get there if you have the right kind of tools. And we're going to talk about that presently. Anyway, so now we go beyond the atomic scale to very large networks. These networks organize themselves so that they will be in there will be as little stress as possible. And actually, the thing that's pretty is that it had been known for a long, long time that there are all kinds of phase transitions, for instance, the liquid-gas transition, among equilibrium systems. But what we found was that these glasses also have phase transitions, and they separate, however, into two kinds of subphases on a nanoscale, that is to say, on a scale of 10 angstroms or so. And these phases are classified as either rigid or flexible. So it's rather like reinforced concrete. You have, as you know, the way reinforced concrete works, concrete's kind of a not very stable material against shear. So what you do is you run iron rods through it, and that reinforces the concrete and gives it rigidity against shear forces. Well, that's basically what we finally found out that was what was happening in the glass, and we were able to confirm that by experiment. And this again, as I say, this very large system turns out to be guided by very simple problems, very simple mechanisms. And this actually shows this stiffness idea where we measure a vibrational frequency of some atoms against composition, and you can see that when there are too few constraints, it's softer, and when there are too many constraints, it becomes more rigid, and there's a very abrupt transition from soft to rigid, flexible to rigid. And that's on the left there, and on the right, over something like, if you look here, you'll see there are three different, he's making samples, but he's having trouble making a really good sample. In material science, the difference between really good and what graduate students' first effort is pretty big. So, and in this case, it took him many years. You see, he starts out here in 1997, 2009, 2011, and eventually he finds that there is a phase, not only a phase transition, but an intermediate phase. And this intermediate phase has a perfectly reversible, you notice that what we have plotted over here on the ordinate is the non-reversible entropy of the glass transition, which turns out to be very small in this narrow window. Now that narrow window is very important because that also happens to be the window where it turns out, I'm not showing it, it also turns out in this region where the stress is very small. And that narrow window is what makes it possible to build skyscrapers out of window glass without any reinforcing rods in them. So we finally think we've caught up with technology, and in fact, all these ideas, I was very happy about this, all these ideas have been adopted by Corning and Nippon Electric Glass, and they've changed the theory of glass as practiced in industry. This is not students or professors or somebody writing an academic paper. This stuff is all used now in industry. These glass industries have huge databases, and the way they were organizing them was using a theory from the 1920s. That theory has been superseded by this theory based on constraints, and it's the first change in industrial practical glass theory in 80 years. So we're pretty pleased about that. And at a more aesthetic level, we were actually able to predict where these windows would come on the phase diagram with an accuracy of about 1%. And you can't do that in any other kind of equilibrium phase diagram. So doing this for a non-equilibrium system was a revelation. As I say, it took 30 years. But it was worth it because we finally convinced ourselves we could solve these impossible problems. This is very important, and we realized that networks are not as hard as people thought they were. Okay. Now, I'm going to talk about another aspect of these glasses, which is the statistical aspect. And we talk about what their statistics look like. Now, there are all kinds of statistics, exponential statistics, Gaussian, which is sort of an exponential squared, and so on and so forth. But what I got interested in was the statistics for the relaxation of glasses. This is a non-equilibrium system, relaxes in a strange way, with a long tail in the statistics of the relaxation, that's the black swan, the fat tail. You get a long tail in the glasses. And the function that actually is known to explain this is a stretched exponential. This is it. And beta here is, you notice it looks like an exponential, but the argument here is to a fractional power. Beta is a fraction between 0 and 1. And we worked out a theory for what the fraction should be. Now, it says here what the two fractions are and why they hold. I should say something about this. These are magic numbers. They're pure numbers. They don't depend on any of the fundamental physical constants. They're just pure numbers. And there aren't any pure numbers in physics outside of quantum phenomena, except for these. These are the first two pure numbers in physics that have ever been found for non-quantum phenomena. And the fact that we found them in the context of the relaxation statistics of glasses has been a big surprise to a lot of people. And they are, generally speaking, quite upset about it. I love it. You know, épatez la bourgeoisie. Anyway, stick it to the guys. Anyway, so now what happened here? Well, this is where it begins to get a little hard. The little hard part is that all of these things work only if you understand homogeneous and inhomogeneous. And most people sort of cut corners here. They look at equilibrium systems, like the liquid-glass transition, where you can work it out. A certain fraction is liquid, a certain fraction is gas. Fine. They work it out for crystals. Nice thing about crystals is you can grow crystals to be almost perfectly homogeneous. Silicon crystals are very, very homogeneous if you want them to be, or you occasionally put in a little impurity where you want it. That's the basis of all of our electronic nanotechnology and optoelectronic nanotech. Anyway, in the glass, what happens is you have to worry about the glass is not perfect, it's not in equilibrium. Even without putting impurities in, it won't be perfect, and there will be traps. And the excitations associated with the relaxation that I talked about diffuse to these traps. And I talked on the previous slide about short steps and long steps. And one of them was short steps, one situation. The other is a mixture of short and long steps. And we worked these out, and we changed the diffusion equation, and we found these magic numbers. And we got a payoff that is characteristic of big data. Somebody has taken the citations of all the scientific literature of the 20th century, which is 25 million papers, 600 million citations. That's a lot of stuff. But, you know, with computers, you collect it all, you can process it, and they work out what the relaxation was. And the amazing thing, the amazing thing here was that the two magic numbers I had, one of them applied to the distribution of these statistics before 1960, and the other one applied after 1960. I was pretty pleased when I saw this, because this paper doing the statistics of the scientific network, that paper came out a couple of years ago, and my theory had come out 15 years ago. So I think I could legitimately say I did it first. I even predicted it, except I never thought of applying it to scientific knowledge. But it works. And you may, now at this point, everybody has to pause and say, what happened in 1960 that would make this distribution change abruptly? Well, having been there, you know, I'm so old, I was there in 1960. I know what happened. What happened was two things. First of all, we got to the space age, and everybody suddenly got interested in science, a lot more interested than they were before. And secondly, we got jet planes. So all of a sudden, the government was paying scientists to take vacations, transatlantic vacations, and that's the long hop. Technically, it's a funny thing. They're called Levy flights, and that's kind of, the mathematicians just think of them as long hops. But in our case, the scientists were actually getting on planes and taking a flight across the Atlantic. Anyway, that's what happened in 1960, and it made it switch from 3/5 to 3/7. And that was a neat one, right? Once you get the handle on networks, you can do amazing things. So here's the plot. This is the citations per paper. Now, some papers have more, some have less, and this is the distributions. Anyway, you got globalization, the space race, commercial jets, and you can see less than 1960, after 1960. Now, this isn't the only example. Once you get into this, you find lots of examples. Turns out there are more than 100 countries with population distributions, and they're fit with beta with a stretched exponent. What else? My stretched exponential is everywhere. There we are. Good old beta equals 3/7. Why beta equals 3/7? Because there's a lot of migration going on. And if I look around the audience, I see a lot of people who have in fact migrated. So you're part of one here. You fit, I'm sorry about that, You ought like to think you're individual and special, actually just part of a statistical distribution. You can be individual and special in other ways, though. But on this particular point, the large-scale migration, that is mainly fitted by this thing. Then now comes a really tricky one. I thought this is beautiful. Suppose, everybody's growing food and they're shipping it to any customer wherever, right? Well, so long as it's just, you measure the amount of food trade and the amount of food exported or imported by a given country, you get simple exponential distribution, which physically means you sell your food to anybody who wants to buy it. But the question is, which crop should you grow? Should you grow corn or soybeans? Now, the crop you grow depends on the resources you have available. Turns out there's only one resource that really matters, and that's water. If you re-express this global food trade in terms of how much water it costs to produce a certain amount of corn or a certain amount of soybeans, in other words, what's called the virtual global water equivalent. There are specialists who work on this kind of problem. They collected all the data, they worked it all out, and they got a distribution, and they found out that when you expressed it in terms of the virtual water equivalent instead of just the value of the crop, that you got beta equals 3/7. Hey, that's my 3/7. And there's an old saying. I come from a desert part of the United States, New Mexico. There's an old saying out west, you never notice the water till the well runs dry. So water is the crucial thing that dominates global food strategies. And the neat thing here is it's not a matter of opinion, it comes out of the statistics. So all of this started out, remember, we started out working on glass. We ended up with the network of global food trade and how it's re-expressed in terms of water. That's magic, right? Neat. Okay. Next. Now we're going to go over to this subject which physicists love and nobody else really cares much about, except it actually has had a lot of spin-offs. It turns out that these oxides and ceramics and so on are now changing in a way that we could never have understood before. For instance, Corning has changed a lot. I mentioned that they like my theory. That isn't all. They are producing all kinds of new kinds of glasses, and they're treating this in a scientific way, and it's not just stir it up and run out a window pane anymore. It's quite a different thing. They have all kinds of specialty glasses which do all kinds of wonderful things, but I can't tell you about them now. What I'm going to tell you about is this special thing, the high-temperature superconductors, which have certain transition temperatures. Now this tells you, whoops, I keep hitting the wrong button. But anyway, this explains what superconductivity is about, how special it is. And this high-temperature superconductivity, which moved from quite low temperatures up to almost half of room temperature, which is very high. And a lot of theorists were blown away by this. As a matter of fact, I counted 10 Nobel laureate theorists gave explanations for this based on what they knew, which wasn't much, and they were all wrong. That's because they were basing their explanations on what they knew from the small data. But as soon as this great discovery was made, people began to collect a lot of data, and by now, definitely in the big data category. I counted someplace between 50,000 and 100,000 papers on this subject. So that's a lot of data. And when you put it all together, you realize that the only way these very high temperatures can be occurring is if the conducting paths in these oxides, they're not metals in the usual sense, but there are still conductive paths if they form a self-organized network. And you think about that, and then you think, well, what really matters is the highest temperature that you can get, and that will depend on the connectivity of the network, and that quantity down there, average value of R, is the average coordination number for the network. The whole thing, just average, and it works. You see, we get a beautiful plot of the maximum transition temperature for using this as a configuration coordinate, this average connectivity of the network, which has upset a lot of people because this is not the way they wanted to think about it. They were trying to think about it in terms of something connected with the old metallic theory, which is just plain not right. This is a network, and it has an average connectivity, and this is it. And you see that you get this nice peak, boom. Now what I liked particularly about this was, first of all, you have to realize that you want to make this kind of plot, and that the correct configuration coordinate is the average connectivity of the network. That's not obvious at all. But I decided, why not try it? You know, it's the simplest possible thing. That's what Shockley said I should do. So let me try the simplest possible thing and plot it up. And of course, it worked the first time. I love that kind of theory that works the first time, where you don't have to fudge around in order to get something publishable. It just falls right out, providing you're brave enough to do something impossible, which is try this idea. Now, the nicest part about it, I don't know whether you can see it here, but at the time that I made the plot, you see this is oxides on this side. That's what the O stands for, and then there are other elements, but they're all oxides. Over on this side, you see oxygen and fluorine, or oxygen and chlorine. In other words, you see, if you know a little bit about the periodic table, that these are oxyhalides, which are really scary. I mean, if you know any chemistry, mixing oxygen and a halogen to form a network, that's not like an oxide anymore. It's very different. Anyway, you see it's nice and symmetrical. That's one of the beauties. And I looked and I said, well, it looks mostly symmetrical, except this one point, which had just been published. They just made this compound. I didn't believe it. I said, yeah, it's just the first publication. I bet I should draw this dashed line symmetrically. And I did draw it that way and published it. And the next year, they came out with a better crystal right here. And if you can look closely, that's a smiling face. That's my face. Smiling at the fact that I predicted this temperature to within about 3%. And this point was way too low. So that was nice. I loved it. But it was all part of a self-organized compacted network. In other words, I was on a roll, and I had a good thing going. Okay. Now we're going to go on to the big show. The big show, these things are all very nice. I mean, can't get around it. But the big show is proteins and life itself. And one of my ancestors as a theoretical physicist was Erwin Schrödinger. You may have heard of him because he invented a large part of quantum mechanics. And he was German, and he spent, naturally, he was stuck in Germany during World War II. And rather than go nuts, he thought about what kind of science would he like to do after the war was over. And he wrote a book about it, and when the war was over, he published it. And it was called What is Life? And he thought about how you would do a theory of life if you were a theoretical physicist and had no data, which was the situation in 1945. And he wrote a very interesting book, and he tried to explain how you would do it. Now, in fact, the book has not, the ideas in it were very misty, but they did inspire a lot of physicists to say, well, he's asking a good question. Shortly thereafter, we got people doing protein crystal structures of hemoglobin. We got Crick and Watson doing the structure of DNA, and we got Pauling's alpha helix. So I think it's fair to say that Schrodinger's imagination in writing that book did push a lot of the science, both physicists and chemists, into proteins after the end of the Second War. Okay, now what we know about proteins, and this has been known for quite a long time, is, and I keep doing this, is that they are compacted by interactions with water. Well, it's a long polymer consisting of peptide subunits, which you don't need to know too much about, and an amino acid side group. And there are 20 amino acids, and the typical protein has about 350 side groups. That's a long chain with a lot of side groups, and it sounds like an impossible problem. However, all of these proteins are compacted by water. That's what they all share, a common feature, which is they collapse into globules because of the water. So now we have these amino acids, and the protein is formally described as a coded message with about 350 letters. Since there are only 20 amino acids and 26 letters, you see we have enough letter to have one for each amino acid. So you look at this thing, and there it is, right? But it's a message about how that protein functions, but it's expressed in a code. The question is, can we break the code? The answer is yes. I wouldn't be talking about it if the answer were no. So how do we do that? Well, what we know is, in this very old idea, is that the reason the protein collapses into a globule is some of the amino acids, some of the amino acids like water and some don't, and that's the way it goes. And I will not go through this any further. I have some things I want to say to the students, so I'm going to, since I've been told I've been too slow, is there a magic way to quantify these interactions? Yes, there is, and I go on and explain how I do it. It works. I've been working on it, and I'm now convinced the methods I'm using are accurate to 3 nines, so I won't go how I do it. That's my magic hydrophobicity wand, and it works. And we did, oh, wait, we have to go back. And I've done a lot of stuff. We ran out of time. I want to go to this last parable. So it's about Alice. Alice is, she says, there's no use trying. She says, one can't believe in impossible things. And the Queen says, I dare say you haven't had much practice. When I was younger, I always did it for half an hour a day. Why, sometimes I've believed as many as 6 impossible things before breakfast. And that brings us to you. So I have some prescriptions for the students. Prescriptions for the world of big and bigger data. There's a lot of data out there already. There's going to be a lot more. It's coming in a flood every year or two, whole new thing. So if I were an NJIT student today, what would I do to face this? Well, I could say, give up and let myself be drowned. But if you're here, you're not giving up. You're trying, in fact, to prepare yourself for exactly this problem, the world of big and bigger data. So I'm speaking for myself. I'm a physicist. And I'm even a theoretical physicist, so I'm biased. But people used to say theoretical physicists were useless. They also used to say mathematicians are useless. Today, mathematicians run hedge funds, and they're billionaires, right? So mathematics isn't useless the way it used to be when you have a world of big data, and theoretical physics isn't useless the way it used to be if you have a world of bigger and bigger data. But even so, if you're going to do this, I'm not saying you want to do this, but if you are thinking about doing it, what you have to do is, I'm talking about undergraduates. You can do the same thing for graduates. I do a double major in applied physics and computer science. I know some young people who've done this, and they're doing very well. So that's what they did, a double major of applied physics and computer science. And I looked in the NJIT program for applied physics, and they said, well, you should go to chem lab. A little chemistry is good for the soul. Well, yeah, but I never did very well in chem lab, and I never used it. And I wouldn't worry. I don't think you really need that, at least for the world of big data. I'd throw out chem lab. I'd throw out electricity and magnetism. I don't need that. Beautiful. Maxwell's equations. You can't beat it, right? They're beautiful, beautiful. Double E is taking care of that subject. So I do my double major in applied physics and computer science. I'd throw in 2 or 3 courses in statistics, not because I really think that they're the answer to a world of big data. They're not. But they're what you have to get started. I mean, it's a tool. If you don't know the language, you're not going to understand what people are talking about. So you have to do it. But the great thing is, a certain kind of mathematics is used in computer science. And that is very good training. I won't go into the logic of it, but computer science is built around a very special kind of mathematics that, of course, is marvelous for handling big data. That's what computer science turns out, and that's what it uses. Now, so if you do all this, I think you're basically in business. There's one last remark. Why do applied physics at all? Why not just do computer science and statistics and skip the science part altogether? Well, the answer is, it's one thing to be a programmer. It's another thing to know statistics. But if you're going to live in this world of big and bigger data, you need to have ideas, and you need to be able to solve problems. And the question is, it's just like the Queen said, it's how much practice you get. She used to practice it every day, remember? So if you're going to solve impossible problems, you have to have practice. Where can you get the practice? The best place to get practice is in those homework problems in physics, because they're logical, they're well-defined, and they require just a little extra something from you. When you go out into the world of big and bigger data, it's that little extra something that you're going to need to get a good idea, which you will then program, knowing computer science. You'll check it out by comparing it against the statistics, and you'll see your idea is better than the statistics. That's your base mark, right? You start with your benchmark of statistics. You get a simple little idea that you think of because you've learned how to solve problems. And the next thing you know, you're in business. So I'll stop there.